Yeah, so this talk is about climate resilient agriculture and how we are using Postgres and PostGIS for our project that we are working on. So this is going to be not merely a technical talk. We are going to share our experiences from rural Maharashtra as part of this project, because that is very important to set the context in the way we are working. So in a moment we will introduce ourselves, but let's first look at the outline. So to set the context, we'll look at what project, we'll try to define the project that we are working on and define the problem of climate resilient agriculture per se. So what exactly climate change, how exactly it impacts in agriculture. And then we'll present a water budget framework, which is a tool developed by IIT Bombay to help combat or help enhance the climate resilience within the agricultural sector in rural Maharashtra. And then we will also look at a tool to help perform farmer surveys in order to capture the reality that exists in the villages. And then finally we'll summarize the findings. Okay. So who are we? Myself, Asim, and my friend Samir, we work together on this project. We are here, but I am a consultant and Samir is a student. He is pursuing BTech in electrical at IIT Bombay, and we are a big team. We are faculty, we are some field staff, students, consultants, and the principal investigator is Professor Milind Soni of the Department of Computer Engineering at IIT Bombay. And so some of the pictures illustrate our team. The first picture here on the left is our team leader conducting a village meeting, presenting our findings. Then the next picture is our field staff looking at irrigation infrastructure and surveying it, noting certain things down. And the last one on the right, the rightmost picture, is our field staff conducting farmer interviews. Okay, so that's who we are. And what is POCRA? By the way, POCRA is an acronym. It stands for Project on Climate Resilient Agriculture. It is funded by the World Bank. World Bank gave a loan to the tune of $600 million to the State Department of Agriculture, Maharashtra. And since 2018, IIT Bombay has been involved with this project. We have signed a series of 5 MOUs, 1 MOU per year roughly, and all our contracts are public. You can access them from the link down there. So the main objective of this project, as per the World Bank definition, is to improve climate resilience of smallholder farmers. And the project region is shown in the map on the right. It comprises 15 districts of central Maharashtra, and not all villages in those districts are covered. Total number of villages covered by the project is 5,000. So yeah, let's now understand climate change in the context of agriculture. Okay, the two key events of climate change are dry spells and wet spells. Like in this monsoon, in the entire month of August was dry, at least in central Maharashtra, and that the picture on the right is a village in district Beed in central Maharashtra. You can see the cotton that is below the knee level, right? And usually, and this survey was conducted, this is in October 2023. So typically in October 2023, cotton should be of this height, at least this height, but it is this. So clearly you can see, which then results in complete yield loss to the tune of what, 70% roughly. And the picture below is a different village. It's Tembha in Wardha district, and that village is facing the other problem of climate change, which is wet spell. So it received, the village received torrential rain to the tune of, let's say, more than 100 millimeters in an hour. So the 124 mm in 1 hour is another example in Yavatmal, which was received on 22nd of July, this last monsoon. So what does such a event result in? You can see in the picture below, which is almost half of his farm is waterlogged and the crop is gone, right? So that's yield loss of 40%. So these are the two main events of climate change when it comes to agriculture, and who are the most impacted here is the small farmers who entirely depend on agriculture, like who don't have, say, a family member working in the cities, earning alternative income, and so on. So that's the context. And the third point that is probably the most important is that village level variation. So climate impact climate impacts differently, climate events impact differently within a single village. As you can see in the charts on the right, the two graphs, the two charts are from the same village. The chart on the top is from shallow soil. So in this village Limba, again in Beed district, there are two kinds of soils, shallow soil and deep soil. And in the region where there is shallow soil, you can see the red line indicates the crop requirement, okay, and the blue line indicates the actual crop uptake, right? And you can see in this, can I point? Yeah, oh, no. Wow, okay. So this gap I wanted to show. This is the gap in the demand versus uptake, right? And this gap coincides with the dry spell. So if you see on the x-axis, this is days, and this dry spell coincides. This region covers the August month, and there is the entire month was almost dry, and so because of this dry spell, the shallow soil got so much impacted. The crop could not take water, whereas the deep soil, the blue line and red lines, they continue to overlap with each other for a longer duration, right? So these two charts highlight the significant variation within the same village because of climate events. And so then we have this questions, right? How do we quantify vulnerability climate vulnerability within a village? How do we and then how do we improve it, right? Quantification and then coming up with a strategy to improve. So based on these observations, we and by the way, what is the current strategy to deal with climate change by the State Department of Agriculture? So this year they announced 10,000 crores as relief package for agriculture. Now, do we have a sound methodology to ensure that these 10,000 crores are going down to the right deserving farmers? And the answer is clearly no. The current method that is adopted by the Department of Agriculture is based on some British era methodology, which was actually founded on usurping as much as possible, right? So that's what we are continuing to use today. So lived reality remains grim, and that is why we come up with a strategy to consider village as a unit when we want to tackle climate change. We cannot. So the first step is to capture the lived reality, right? Establish a baseline. So we go to the villages, conduct farmer surveys, find out how many people, farmers are solely dependent on agriculture, how many farmers have a well, a source of irrigation, how many farmers do not have a well, and those who have a well, how soon the wells run dry. So this map on the right, it shows the map of a village, the village is called Hivar Gawand, again in Beed, and the polygons with the number they are farm plots. They are cadastres, right? Individually owned farm plots. And the solid lines represent streams. They're the solid black lines that cut through those polygons. So here we can see that the first legend entry is no source. So the pink color, this color, represents all the farm plots that do not have any source of irrigation, like a well. So they are completely rain fed. And then the remaining colors represent farm plots that have wells, but how soon the wells run dry, right? So this kind of reality we need to capture. And by the way, this map was generated with Postgres and PostGIS. So the next step is to model biophysical vulnerability. The previous slide we saw that within a village there is so much of variation based on soil type and so on. So we have built a model called water budget framework, which captures this biophysical vulnerability. More details can be found at the two papers that are, the first paper is published in Water Policy Journal and the second paper is from Communications of the ACM. You can have a look for more details, but we'll talk about the water budget model briefly here. Okay, and then finally our objective is to make sure that the Department of Agriculture can tackle this climate change effectively, right, through advisories, through interventions, and so on. So that's what we are trying to achieve here. Yeah, and when it comes to making it work at scale, that's where Postgres comes in. So the 20,000 districts that, the 20,000 villages covered by the project region, we are deploying our model using Postgres and PostGIS at that scale. So yeah, again the same slide, but the first part, to capture the baseline, we need boots on the ground. The second part, biophysical vulnerability, is captured by the water budget model, and then the adoption of it within the Department of Agriculture or within village community is facilitated by a front end, which shows certain maps and so on, which are actionable. Okay. And all of this is backed by Postgres and PostGIS. So let's take a look at the water budget model. Now imagine, all of you, imagine that you're standing on a farm, and what's beneath you is a soil column. And then what happens to the rainfall that falls on that soil column? So this is a little bit of domain specific thing for context setting. So the rainfall gets distributed into multiple components, and those components are shown here. The part of the rainfall, when it falls, it runs off from the surface. Then part of it is infiltrates, and that infiltrated rainfall is available as soil moisture to the crop roots, and the plant roots take that up, and which is called as crop uptake. And that the water that is taken up by plant roots evaporates through the plant leaves. And there are models to capture all these, capture and estimate or quantify all these components, which we are building, and we have built internally. And the soil moisture or the infiltration that further percolates down is, it contributes to groundwater recharge. Okay, so that groundwater recharge is then available through dug wells for irrigation in the next season, post monsoon season. So what we have built is a model that estimates or quantifies or simulates all these components based on hourly rainfall data that we gather from weather stations. So imagine that the soil column on which you are standing, or the point in the farm that you are standing, if you have access to the hourly rainfall or hourly weather data, then we can simulate at each hour what is the state of all those 4 components, right? And that's exactly what our model is trying to do here. But it requires lots of inputs, soil properties, for example, soil texture, soil depth, and so on. And then terrain properties, what is the slope at that point, and so on. So all these properties are encoded as inputs in our PostGIS tables, and then we generate certain output, which are the 4 components that we just saw. So that AET is actually crop uptake, and the crop water deficit, that's one of the most important components that is generated as output by our model. That deficit represents the, as the name suggests, how much how much finally the crop managed to uptake from soil moisture, and that indicates, that directly relates to the yield, the loss of yield. Higher the deficit, higher is the yield loss, and higher is the vulnerability. So yeah, we do this model for, so now we are clear on the computations conducted at a single point. So we do this for the entire project region by overlaying a grid of 200 meter by 200 meter, which is again configurable, but we thought that 200 meters is a good number. So 200 meters squares are overlaid on top of the entire project region, and at the centroid of each square we evaluate the computations that we just saw. Okay, and yeah, so some numbers to give you an idea of what this scale looks like. So right, so then the most important input for our water budget model comes from hourly weather data. Now SkyMet is a private weather provider with which the Department of Agriculture has contracted, and they give us a HTTP API that we hit at 5 AM every day to obtain the weather data from all these rain circles, the weather stations. The red dots in this map represent the weather stations, and the gray, actually the gray lines are actually polygons that are not visible because we have zoomed out too much, but those polygons are individual villages. So what we are looking at is 20,000 villages and 15 districts within central Maharashtra. Okay, so the SkyMet API is in JSON format. We get 2 components from the SkyMet API, which is first one is the station details. Station details includes the latitude and longitude of the station, which we map to the geometry column of the weather stations table, and then hourly weather table is a dynamic table that gets updated, that gets new records for 24 new records for every weather station every day. So typically some weather stations do go down for whatever reasons, so we receive null values, but our model does not tolerate null values or missing data. So then we have, again we used some queries in Postgres and PostGIS to smoothen out the null missing values, and typically that is done by nearest weather station. So let's say at say 7 AM one value is missing from a station, then we get it from the next nearest weather station. If even that station was down at the time, then we go to the next nearest station, and so on. The next set of inputs is the raster data. So we need a bunch of raster data sets, soil depth, soil texture, slope, and elevation. Okay, and soil texture is actually in the form of 3 different parameters, which is the content of silt, content of clay, and content of sand. So and all these raster data sets are supplied by the Department of Agriculture through various agencies, and those are supplied in TIFF format. The raster, typically the most common raster data format is TIFF. We load it using raster to PGSQL, that's the tool, PostGIS tool, and we load it into a big table because these TIFF files are not clipped at district boundaries, whereas our model operates at district boundaries. We process one district at a time. So we need to clip the input data set, at district boundaries and generate district-wise rasters. So the queries on the right-hand side, you can see some PostGIS constructs being used, st intersect, st buffer, and here the interesting part is what this query is doing is it is taking the district boundary as a polygon and creating a buffer around it, which means buffer of what, 100 meters. So the district boundary is expanded by 100 meters from all sides, and then it is overlaid on top of a raster table to clip the raster, and a new table is generated which contains the smaller data set. And then once we have the district wise rasters for each of the input parameters, we need to each grid point in that district, remember the points table, that points table needs to contain needs to be joined with this raster table so that each point gets the raster value at that point. Now this is how do we compute the value at a point? Now remember that our point is a 200 meter by 200 meter square. Now within that point, within that square, it is possible that multiple raster pixels can be contained in, because typically the raster resolution is 30 meters or 5 meters. So if it's a 30 meter raster, then several cells, several pixels will be contained within a 200 meter by 200 meter grid cell for our point table. So then we compute average of all the pixels that are contained within the cell as the value of that parameter for that table. So for example, here we are computing soil depth on the right hand side, soil depth as the average of the mean soil depth of all the pixels that are contained within our grid cell for every grid cell. St summary stats is the function that computes the mean. By the way, you can stop me if you have any questions or need clarifications. The next set of inputs is vector inputs. Now the main vector inputs are administrative boundaries, which is village, taluka, district boundaries, and the other thing is land use, land cover. Now this is a very common terminology used in the remote sensing world, LULC. It provides, so this is a vector data set that we have received from the Department of Agriculture. We simply join it with the points table using st contains properly. St contains properly means within a land use polygon, say the land use data set has classifications such as agriculture, whether this particular polygon represents agriculture land or forest land or say water bodies or habitation and so on. So we overlay this data on top of our points table and assign the land use classification to each point that is contained in the respective land use polygon. Okay, right, and then we need to assign to each village polygon, we need to assign the nearest weather station. Now we have two data sets, right? One is village polygon, it's a geometry vector table, polygon geometry, and weather stations table, which is again a point geometry table. So we are using cross join lateral here to compute the cross join lateral with a limit clause to and using the distance operator. The this is a PostGIS operator. It operates, it computes the distance between two geometries. So in this case, we are feeding one, the geometry on the left hand side is a polygon and geometry on the right hand side is a point. So it takes the centroid of the polygon and computes the distance with the point on the right hand side. And then finally the output table, right? What parameters do we have for the output table? We already saw how the rainfall is broken down into components. These are the same components on the down here: groundwater recharge, runoff, soil moisture, deficit, and uptake. But these are the two important points: the date and crop. We remember that we evaluate this model every day. At 5 a.m. we get the hourly weather data for the previous 24 hours, and we compute the based on that data, we compute the current state and create new entries in the output table for this day, for the day for which we process the weather. And crop, now for this entire 15 districts, at the time of ongoing monsoon, the department does not have the data on which crop is growing at which point. Therefore, what we need to do is we have identified major crops that are grown in central Maharashtra, and those are 32 major crops within our repository. We have modeled their life cycle and what kind of crop demand, crop water requirement we have. Yes, yeah, let's quickly finish it. So yeah, so that's why we need multiple crops. We simulate all crops, and then when we have the data for cropping pattern data, then we can aggregate it. So this is the daily cadence, which we already talked about, and let's look at how this output can be used, right? One use case is once the monsoon season has ended, we look at the water budget for at the end of the monsoon, the day when the monsoon ends, maybe 31st of October, right? And on that day, we compute the volumetric parameters based on the water budget output. The water budget output contains values in millimeters. The soil column, remember, soil column is a one-dimensional thing. So everything you get, groundwater recharge and all these parameters are in millimeters. Now those quantities are converted into volume by using the village area, right? And now we are talking about one specific village. So for that village, what is the volumetric and then once we compute this volumetric water budget, we can arrive at certain interesting numbers, such as, say, let's go to Hivargavan again. So in Hivargavan, on 31st of October, the green highlighted numbers, if you sum them up, that is the total volume of water available for the post-monsoon season, which is Rabi season. Now, if you divide that by the area of the village, it means that, sorry, not divide by the area, divide by the crop demand. So typically, gram crop requires 300 millimeters of water throughout its life cycle. So if the entire village plants gram or chana, then what we can expect is only 156 or 29% of the agricultural land can be covered by this crop. Otherwise, the rest, if you plant more, then that crop will suffer because it will not get enough water. 300 mm of water will not be available. So then so water budget, what we just saw is water budget enables sustainable cropping pattern for the village to be arrived at, right? And we actually tried this exercise in 12 villages in the last monsoon. So you can see some images of village meetings being conducted in 5 different villages. So yeah, these are the takeaways from through the village meetings, that we have area under crop and choice of crop. These are the knobs that the village community can control, and for the long term, village community can collaborate with the department to enhance the capacity of the village to impound the runoff. The water that flows out, the rainwater that flows through the streams, that can be impounded and made available for Rabi cropping season. And this is another map that shows year-round Rabi availability. Once you have these results, lots of things can be done. So yeah, with this I will hand over to Samir, who built all the tools that you are going to see.
Hi, hi, I'm Samir. I'm a student and I've been working on the front end side of it a bit. So once we have all these water budget results available to us, we have to make them accessible and palatable to anybody who looks at it. So anybody from the government, when they want to look at these results, we need to create like a advisory stack for them. So for that, we have the backend is basically the database, and we have GeoServer, which is an open source software that can directly read Postgres tables and display those geometries, like a world map. You can look at each district and like something like this. So that's what GeoServer does. The Flask application is used for running PostGIS queries, like how much deficit was there in the last week or month, basically cumulative, and then displaying it, and all of that information is displayed on a web application. So the different versions of this web application for different users. For example, the district view would be useful to like a district level agricultural officer if he wants to think about the agricultural planning for his district. So this is total rain. As you can see, we can also display rainfall in the last 7 days, length of the ongoing dry spell. So total rain would be useful for somebody who's thinking about Rabi water budget planning. So you can know where can we grow a lot of crops and where is there not a lot of water for the Rabi season. And this is length of the ongoing dry spell. So back in August, I think we had almost no rain, so a lot of areas in Bede were affected because of that. So they needed immediate irrigative measures in order to save the yield. And if we go a layer below to the talukas in each district, you can start to see point-wise results. Like all of those are pixels. So you can see point-wise unmet water demand is just the crop water deficit that Asim elaborated on. So again, this is in Latur. So it doesn't look that great because there wasn't a lot of rain in 2023. And once you go another level, you come to the village. So how do you plan at the village? What is the rainfall like? That is from the nearest weather station. And you can also see cadastres-wise plots. Again, those are pixel-wise values. So this was for a certain village in where? In Bede. Yeah. So now, once we have all these water budget results, we need some method of validating our output, going and surveying farmers. But when you have so many villages, 20,000 villages in our project region, 44,000 villages all across Maharashtra, how do we survey? How do we pick which farmers to survey? In any given village, you have like 500 farm plots. So in order to make that decision, we need some kind of tool to pick out, let's say, 40 farm plots out of the 500 with a good spread across multiple criteria like types of soil, elevation, its proximity to a stream, and also a good geographical spread across the entire village in general. So for that, I made a tool which basically creates partitions of the village based on these criteria. So this soil depth partition, soil depth is available to us as a big raster. So I use this ST clip to clip the raster at the village boundary. And then ST reclass is used to classify the raster based on predefined ranges. So as you see, 0 to 25 centimeters of soil depth, I put it into one class. So that's like shallow soil. 25 to 60 is medium soil, and then deep soil. So you get the entire village partition into 3 separate classes. And that's soil depth. And elevation is a bit more nuanced because it varies widely from village to village, sea level. So you have to kind of query the raster within a village, find what the minimum elevation and maximum elevation is, and then I do that using ST pixel as points. So it splits up the raster into pixels, and then I number every single point ordered by their elevation. So we have a ranking now, and then we compute the 33 percentile and 67 percentile classes. So now we have 3 partitions according to elevation, right? So once elevation is done, proximity to streams. So the farm plots closest to the streams would have fertile land. They have access to river water, while the landlocked farms are further away. So we take a buffer around a stream, buffered by the magnitude. Some streams are bigger, some are small, so magnitude captures that size. And then we use ST difference. Again, all these are PostGIS functions, very helpful. ST difference kind of takes the complement of the stream fed region in the village geometry. So we have a partition of stream fed farm plots and landlocked farm plots. And finally we get these, the 3 partitions that we just discussed. And if we intersect all 3 partitions, we get a super partition that divides the entire village into 18 zones. And from those 18 zones, we have to take a good pick of farmers to survey. So that is done by, well, basically a group by, right? Group by elect class, depth well, and stream region. And we also do it by random, order by random, so that if we get an undesirable collection, we can just rerun the script and maybe it'll give us a better collection of farm plots. And to achieve a good geographical spread, what I do is per biophysical zone that's generated, I go through the farm plots in order and drop all the farm plots right next to it. And I can figure out if 2 farm plots are touching using the ST touches algorithm. So that way you get all of them as non-intersecting. I mean, farm plots that don't touch each other, so you get a good spread. And these are the results, right? So now if you want to conduct a survey, you can go to these farms and just do your work.
Okay. In summary, this whatever we saw earlier, the water budget model and the field survey, the survey tool that Samir has built, what we are trying to do is to try to trigger this infinite loop, where the first part is to capture physical reality, generate good quality data, then analyze it, build models, and help address the problems that have come out of that analysis. So that's an infinite loop that we are aspiring for. And this involves the State Department of Agriculture. And this is applicable to many other domains like transportation or drinking water, sanitation, and so on. We have been talking about this AI bandwagon for a long time, but without the real data, the entire rural Maharashtra would be left out of this AI bandwagon, right? So this infinite loop we think is very important. And the Postgres, PostGIS, and the entire geospatial community has really enabled this data-driven decisions at village level. And also we have been able to help the Department of Agriculture exercise their mandate, which is to reach the agricultural community, right? And some similar projects that we are also working on at IIT Bombay are generating accurate maps with the Directorate of Land Records Maharashtra, then quantifying the state of agriculture using a different kind of model called flow-based model, which is actively being built and conceptualized in Himachal Pradesh. Because of the terrain, the same model is not applicable there. And this is with the Forest Department of Himachal Pradesh. And then we have multiple contracts with Ratnagiri district CEO and some other district CEOs as well for road network development, for analyzing their drinking water schemes and so on. So yeah, our team is very much in gratitude with the PostGIS, Postgres contributors. So thank you. Unfortunately, we both have to leave right away for our flight, but please don't hesitate reaching out. And if you want to join our team, you are welcome. Do write us. That's our contact. Thank you. Do we have time for questions or? Okay. Sure, yeah. offline questions.